Hi there, this is Peuntinger and I am B Heim, and we would like to tell you about our quantum communication experiment over a free space point-to-point link of 1.6 kilometers in the city of Erlangen in Germany.
We study atmospheric influences on the capability of the link to act as a continuous variable quantum channel. We use polarization encoding, which is particularly robust against atmospheric influences. This aerial photo gives an impression of a free space link in the city of Erlangen. In a truly urban environment, it connects the building of the Max Planck Institute for the Science of Light with a tall building of the Department of Computer Science of the Friedrich-Alexander University Erlangen-Nuremberg.
The setup of the sender is placed in a technical supply room on the roof of our institute's building. A continuous wave laser beam at a wavelength of 809 nanometers is guided by a polarization-maintaining single-mode fiber to an outcoupling stage on a breadboard. This breadboard is mounted on a rotation tilt stage for beam alignment and can easily be exchanged. A bright circularly polarized beam is sent through two electro-optical modulators, which introduce small signal components in the orthogonal polarization. A half-wave plate in between of these modulators allows to realize a two-dimensional signal state generation, so in principle any modulation format can be used. We focus on the discrete modulation of coherent states that are strongly overlapping and thus nearly indistinguishable. The generated states now contain the signal encoding as well as a local oscillator, polarization multiplexed and in the same spatial mode. This beam is then further guided by two mirrors and expanded by a telescope to a diameter of approximately 4 centimeters. After that, it leaves the sender setup and is sent towards the receiver.
This is an outer view of the sender. On its way to the receiver, that is currently shown, the quantum beam passes buildings, trees and streets. This heterogeneous environment contributes to atmospheric turbulence, by which the beam gets distorted and diverges more than expected by the diffraction limit. We recorded the arriving beam seen on the screen. As you can see, the beam suffers from both wavefront distortions and beam wandering or spatial jitter. The beam is clipped as the receiver aperture is smaller than the jittering arriving beam. Thus the received intensity fluctuates. We were able to increase the overall link transmission to 76%. A telescope is used to demagnify and collimate the arriving beam. The signal states are measured in a double homodyne detection, which in our scheme is realized as a simultaneous measurement of the S1 and S2 Stokes parameters. This directly reveals the Q function of the states. For our polarization multiplexed setting, phase fluctuations are intrinsically autocompensated as both signal and local oscillator undergo the same atmospheric fluctuations. In contrast to single photon detection techniques, the influence of stray light on the scheme is negligible. We finally interpret the measured data by using the framework of effective entanglement and determine optimal working points with respect to the distributed effective entanglement. The high entanglement transmission rates that our system can achieve indicate the strong potential of atmospheric links in the field of continuous variable quantum key distribution.